Now we put it all together to see how the first and second derivatives can help us graph a function. Using derivatives to graph a function. We're going to get through two examples. It'll take us a bit of time. Wanted to start out with a more basic one and then look at one that's maybe a bit more obscure. So let's graph f of x equals 200 plus 8x cubed plus x to the fourth using f prime and f double prime. Okay? So this will mean we'll need to identify places where the function is increasing and decreasing, local maxes and mins, concavity, and inflection points. So the first thing we're going to do is, we recognize that this function is continuous everywhere. It's just a polynomial. It's continuous everywhere. Okay? So that's useful. And then we'll proceed to look at the first derivative, f prime of x equals 24x squared plus 4x to the third. And because we know we're going to be finding the critical numbers and setting this equal to 0, let's go ahead and put it in order and factor it. So I'll put 4x to the third plus 24x squared and then factor. So I can pull out a 4x squared, leaving behind an x plus 6. So the critical numbers here are 0 and negative 6 are the critical numbers. So we'll keep that in mind. Next, let's look at the second derivative. So f double prime of x equals, and we'll differentiate this formula. So we get, actually let's use the one that's in descending order. So we get 12x squared plus 48x. And again, we'll be finding critical numbers of this, so we'll factor out the 12x, leaving behind x plus 4. And so the critical numbers here are 0 and negative 4. All right? Now we're going to create a big chart with all of the critical numbers. We're going to look at f prime, f double prime, and what all of that tells us about f. Okay? So let's get started. So we're going to have a top row. In fact, I suppose we need both of those there. So let's create our top x row. And then beneath that we'll have our f prime row, and then our f double prime row, and then our f row. Okay? I'm going to begin by cutting my x number line at the critical values. Negative 6 is the first one. X equals negative 6. Negative 4 is the next one. X equals negative 4. And then 0 is the next one. Okay? All right. So the critical values for f prime were 0 and negative 6. And those were critical values because they make the derivative equal 0. So I know that f prime is 0 at both of those. Negative 4 is not a critical value, so we're going to ignore that for now. The critical values for f double prime were 0 and negative 4 because those were the values that made f double prime 0. So negative 4, f double prime is 0, and at 0, f double prime is 0. Now we're going to go through, and for f prime, we're going to fill in all of these other spots with positives or negatives. And of course, understanding that here we have the x values that are less than negative 6. Here we have the x values between negative 6 and negative 4. Here between negative 4 and 0. And here we have the x values bigger than 0. Now, all I'm going to do is I'm going to think about which x values I have and how they affect my f prime. So if x is less than negative 6, x plus 6 is negative, x squared is positive. So we have 4 times positive times negative, so f prime is negative. And then we could do the same for the rest of the intervals. Now, the thing that's happening between our two zeros here is all of these signs have to be the same. They can't switch from negative to positive here without creating another zero. So whatever this sign is, all three of these have to be the same. So now if I pick a number between negative 6 and negative 4, this guy is positive. When I square this, it's positive. So I get 4 times positive times positive. So everything between the two zeros here, f prime is positive. And then after 0, this guy's positive, this guy's positive. 4 times positive is still positive. So now we have our f prime row done. F double prime, again, everything to the left of this 0 is going to be the same. Everything between is going to be the same. Everything to the right is going to be the same. So let's look at x values less than negative 6 here. This is negative, and x plus 4 will be negative. So we have 12 times negative times negative. So on this side we have positive. 12 times negative is positive. Then when we pick a number between negative 4 and 0, this is negative, and this is negative. So we have 12 times negative times, let me see one more time here. Sorry, x is negative, but x plus 4 is positive here. So we have 12 times negative times positive, which is negative. Of course, you can pause and figure all these out on your own. The emphasis is not how to figure out the pluses and minuses. Okay, I figure you can do that. I want to put all of this together in this video, though, so I don't want to take forever. Then if I use x values that are bigger than 0, x is positive, x plus 4 is positive, 12 times positive is positive. All right. Now, we can put all of this together to see what we can figure out about f. So here, whenever x is less than negative 6, I know that f prime is negative, so we know f is decreasing. And f double prime is positive, so we are concave up. Here, f prime is 0, so we have a horizontal tangent line, and f double prime is positive, so we're still concave up. F prime is positive, f double prime is positive, so we are increasing and concave up. F prime is positive, f double prime is 0. That just tells us we don't have any concavity there. It doesn't really help us much. But f prime is positive, so we know we're increasing. Okay, no concavity. F prime is positive, f double prime is negative, so we are increasing and concave down. F prime is 0, so we have a horizontal tangent line, and we're not concave at all. We have a f double prime of 0. And last, we're increasing and concave up. Okay? Now, before we go to graphing, let's see what other information we can get. So here, our function goes from decreasing to increasing at negative 6, and we know that the function is continuous. So if we're going from decreasing to increasing, that means that this point at negative 6 is a local minimum. So we need to figure out the value of that. We'll do that momentarily. Let's see. At negative 4, we're increasing, so we don't have a local min or local max. At 0, we're not increasing or decreasing. And we're going from increasing to increasing, right? We're not changing, we're going from increasing to increasing, so we don't have a local min or max there at all. The only candidate for local min or max is where we go from decreasing to increasing or from increasing to decreasing, and that never happens. So we have a local minimum value, and that's it. Now, let's talk about inflection points. Inflection points happen when the concavity changes at a point of continuity. So we're concave up, concave up, concave up, but here we switch from concave up to concave down at negative 4. and we know we're continuous. So here we have an inflection point at -4, comma, and we have to find that y value. So we'll use the calculator shortly to figure out these y values. And then from here, we go concave down to concave up at 0, and we know we're continuous here. So that's another inflection point. Inflection point at 0, comma, whatever the y value is. Now actually this one's very easy because I can easily plug 0 into my f function. The terms with x turn to 0, so I just get 200. So I have an inflection point at 0, 200. Then let's go ahead and find my two y values there. I'm going to do this on my TI-36X Pro. Makes it super easy. So I need to look at x equals -6 first, and then I'm going to plug that into the function. So here's my calculator. I'm going to store -6 in for x. So I'm going to type -6 store and then x and hit enter, and now that's stored in for x. Then I'm going to type my function, which is 200 plus 8x to the third power plus x to the fourth power. And so I'm going to calculate the value of that function whenever x is -6, and I get -232. So that means I can come over here, and my local minimum value at -6 is -232. All right, so now I'm going to do the same thing. I'm not going to come show the camera, but I'm just going to change. I'm going to put -4. I'm going to put -4 store x. And I'm going to use my up arrow to get back to my formula, recalculate it with -4 as my input, and the y value I get there is -56. Okay? So now I've got everything I need to start to put together my graph. I have y values for all of my critical numbers. So let's come over here and try to sketch a graph of f. Let's put all of this together. So now, if I want to graph f, it's not going to be precise. You can see how big those y values are, but I know I need to worry about -6, -4, and 0. So I'm going to be kind of careful about indicating those. So let's say 0's over here. And then I've got -4 and -6, okay? So I know at -6, I've got the y value of -232. So I'll maybe put that down here, -232, oops, at x equals -6. So that's right there. And I know that's going to be a local minimum value. I can also tell it's concave up there, so that's good for a local minimum. Then at -4, -56, which is not nearly as far down, so maybe it's like right there. I know I'm going to have an inflection point. I'm going to be changing from concave up to concave down. And then at 0, 200, maybe that's like right here. I will have another inflection point where I change from concave down to concave up. All right, so let's put it together now. So my function starts off decreasing. So it's going to decrease all the way until it gets to this point at -6. So I know it's going to do this kind of thing. It's also concave up. It's also concave up. So it's going to do something like that. Then at -6, it's concave up, horizontal tangent line. So that makes sense. It's going to be a smooth curve here. It's differentiable. And it's going to go to increasing from -6 all the way up to 0. Actually, it's going to increase the whole time. But it's going to be concave up from -6 to -4. And it's going to switch to concave down right here. So it's going to be concave up. It's going to be bent. It's going to open upward until that point. And then after that point, it's going to shift, not shift, but it's going to bend the other way from -4 to 0. It's going to be concave down like this. So see how that's concave down? So I've got my inflection point here, concave up to concave down. And then at 200, that is not a max or min, so I'm being careful not to indicate that because I know my function keeps increasing in a concave up way. So now it's going to bend back upward, open back upward, and increase. So it's going to look something like that. So I made sure it's all nice and smooth. It's continuous, it's differentiable. I've got my inflection points. My inflection points are indicated, and I've got my local minimum here. And so I've addressed all of the characteristics we've discovered using the first and second derivatives of this particular function. Okay? So this is great exercise practicing those concepts. But what do we do if we don't have a polynomial? So let's look at a slightly more obscure example. Now, there's all kinds of functions you could look at here. So this is going to depend heavily on your algebra and your trig. Okay, so you could certainly encounter a trig function or something else. There's not enough time for me to do examples of all of those. Maybe over the years I'll keep adding examples, but I like to teach the concepts in depth and then let students explore those concepts. All right, so let's do the same thing. Let's see, f of x equals 5x to the 2/3 minus 2x to the 5/3 using f prime and f double prime. Okay, again. So, all right, so the first thing we might want to do is that last polynomial, we didn't know how to factor that. It was that ugly degree 4 polynomial. Now this one's kind of interesting. It's perhaps even uglier. However, we could, like we're going to factor the first derivative and the second derivative anyway. It's not a bad idea to go ahead and factor this guy too, just because. So if we look at f of x, I could pull out an x to the 2/3. And really, this is just going to get us warmed up for the first and second derivatives anyway. So if I pull out an x to the 2/3, that's going to leave behind a 5 here, minus, and if I pull an x to the 2/3 out of x to the 5/3, it leaves behind an x to the 3/3, which is just x to the first. Okay. Again, if I pull an x to the 2/3 out of an x to the 5/3, it leaves behind an x to the 3/3. 3/3 is 1. So this is all we get. And so what this kind of helps us with is it helps us understand where, if we want to set this equal to 0, then it tells me which x values make the function equal 0. Those are going to tell us x-intercepts of the graph. Okay, so we could use that if we wanted to. We may come back to it. But now let's look at f prime of x. F prime of x is power rule. 10/3 x to the negative 1/3 minus 10/3 x to the 2/3. Okay? Now we're going to need to factor this also, and this may be kind of new as well because we've got negative exponents. So we want to pull out the biggest exponent that they both have in common. So you have to look at the smaller of the two exponents, which is x to the negative 1/3, and we can pull that out. And in fact, we could even pull the coefficient of 10/3 out. When we pull out 10/3 x to the negative 1/3, it's going to leave a 1 here, minus, when we pull x to the negative 1/3 out of x to the 2/3, we're dividing. And when you divide, you subtract exponents. So 2/3 minus negative 1/3 is 2/3 plus 1/3, which is 3/3. So we're just left with an x to the 3/3 or x to the first here. Now the easier way to maybe think about that until you get used to it is to think in reverse. If you distributed this back out, in other words, when you multiplied these together, you should get x to the 2/3. So you would add the exponents here. X to the negative 1/3 times x to the first. Well, you'd add negative 1/3 and 1 to get 2/3. And so that's our f prime of x. And we can find the critical numbers for this. The critical numbers are going to be what make it undefined, which here we're dividing by x to the positive 1/3. A negative exponent is the same as division. So 0 is a critical number there because we'd be dividing by 0. And if x is 1, this would be 0, making the entire derivative 0. So those are our critical numbers for f prime. F double prime, we need to differentiate f prime. Power rule tells us we'll have negative 10 thirds x to the negative 4 thirds minus negative 10 ninths. Sorry about that, I almost overlooked it. Negative 10 ninths minus 20 ninths x to the negative 1 third. And again, we're going to factor. I can pull an x to the negative 4 thirds out because that's the smaller of the two exponents, but I can also pull out a negative 10 ninths from both of these. So pull out negative 10 ninths x to the negative 4 thirds. That's going to make this term a 1, plus that's going to make this a 2 when I pull out the 10 ninths, x to the first power. Okay, so again, we're dividing by x to a power, so one of the critical numbers here is going to be 0, and here we're going to get negative 1/2 if we were to solve that for x. All right, very good. So now we've got f prime, f double prime factored, and we've got the critical numbers for f prime and f double prime. Now at this point, we want to make a chart of signs for f prime and f double prime. So we're going to set up our table. So the top row will be our x values. Then below that we'll have f prime, f double prime, and finally f. And we will cut our x number line at our critical numbers, negative 1/2, 0, and then 1. Okay? All right, let's begin with f prime, whose critical numbers are 0 and 1. And at 0, f prime is undefined because remember we're dividing by x to the 1/3 power and we can't divide by 0. So at 0, f prime does not exist. So this function happens to not be differentiable at 0. Now it is continuous everywhere because these are just cube root functions and cube roots are defined everywhere, continuous on their domains, but it's not differentiable everywhere. Okay, then at 1, f prime equals 0. All right. Now let's go ahead and fill in the signs on all the sides of the critical numbers. So we can look at any numbers over here below 0, any x values below 0. And if we wanted, we could specify that these are the x values between negative 1/2 and 0. These are the x values less than negative 1/2. These are the x values between 0 and 1, and these are the x values bigger than 1. So if we look at any x value less than 0, and we plug it in over here, we're going to get a cube root of a negative number, which is negative, and 1 minus something less than 0 is positive. So we've got 10 thirds times a negative times a positive, so that means that's a negative. If x is between 0 and 1, the cube root of a positive number is positive, and 1 minus something less than 1 is positive. So 10 thirds times positive is positive. And finally, if x is bigger than 1, the cube root of a positive number is positive, but 1 minus something bigger than 1 is negative. So we've got a positive times a negative, so f prime is negative. And let's go ahead and list what we know about the function f at this point based on those signs. Here, f prime is negative, meaning that f is decreasing. So we know each of these intervals, f is decreasing. Here, f is increasing, and here, f is decreasing again. Okay? Furthermore, if f prime is 0, we know that we have a horizontal tangent line. And here f prime does not exist. So it's not differentiable there. We can make a note of that. Not differentiable. And that could be that there's a sharp point. There could be a vertical tangent line. We know it's continuous, so that's not the issue. So it's either a sharp point or a vertical tangent line. In this case, because these are cube roots, my gut is telling me a vertical tangent line. Okay. All right. So now let's work on f double prime and look at its critical values, which are 0 and -1/2. At 0, again, we're dividing by 0 here because this is 1 over a cube root to the 4th power in this case, but you get 1 over 0, which is undefined, so the second derivative does not exist at 0 either. And then at -1/2, this guy is 0, so when you multiply all this together, you get 0. All right? So there are the values, the critical values for f double prime. Now we look at the signs in between the critical values. To the left of -1/2, here we've got a cube root of a negative, so that's negative. And if we plug something smaller than -1/2 in for x here, we're going to get 1 plus a bigger negative number, so this will be negative. So we've got a negative times a negative 10/9 times a negative times a negative. That is negative. Okay? Then if we plug in something between -1/2 and 0, the cube root part is still negative, but now this guy is positive. So we've got negative, negative, positive, which is positive. And then once we get past 0, any number bigger than 0, we're going to get a cube root of a positive, and we're going to get 1 plus a positive. So that's a negative 10/9 times a positive, which is negative to the right of that critical number. And so now, f double prime's negative tells us we're concave down. F double prime being 0 tells us nothing. We don't have any concavity. So it's basically a straight line right there. Here we're concave up. Here we're concave down all for the rest of the way. Okay? All right, now let's do some analysis of f prime, or let's do some analysis here to find local maxes and mins. And we have a candidate for a local max or min here because we're switching from decreasing to increasing. It's continuous at 0. It's not differentiable, but it is continuous. So we know that when we go from decreasing to increasing, we're going to have a local minimum. So here we have a local minimum value. Okay? And then here we're going from increasing to decreasing. We're going from increasing to decreasing. And in this particular case, we're continuous at 1 again, so we're going from increasing to decreasing. So now we have a local max at this point. So we need to find the local max value. We'll do that shortly. Okay. So that's local maxes and mins. Let's use what we know about concavity to identify inflection points. So here we're going from concave down to concave up at -1/2, and this function is continuous there. So that is an inflection point. That's an inflection point. And the x value is -1/2. We'll have to figure out the y, okay? Here we're going from concave up to concave down at 0, where it's also continuous. So this is not only a local minimum, but it's also an inflection point. And the x value is 0, and the y value we have to find. And it will be the same as the y value that we need to find up here for the local minimum value. And then from then on, we are concave down the rest of the way. Okay? So no more inflection points. Now it's a matter of locating those y values. So I'm going to use my calculator. I'm not going to bring it to the camera this time, but I'll start by using -1/2 and storing that in for x. And then I will type my f of x function to calculate my y. So my f of x function is 5x to the 2/3 minus 2x to the 5/3. If I calculate that at -1/2, It looks like I'm going to have to round this. So the alternative here is to literally write this expression with -1/2 in for x. Okay, so you could totally do that, write -1/2 in there for x. But just for simplicity, I'm going to round, so I'll put approximately 3.8 here. Okay? And then at 0, we can figure that one out, right? If we plug 0 in here, we get 0 minus 0. So we actually get 0 as the y value here. No problem there. And next, I need to plug 1 in. That one's also easy to do with the calculator. 1 to the 2/3 is 1. 1 to the 5/3 is 1. So we just get 5 minus 2, which is 3. Okay, so we've got all of the information we're going to need to sketch a graph of this function. And what I'm going to do is I'll leave the factored version of it too, because that could be useful. If it factors and you can easily find x-intercepts, you might as well do it. But here I need to indicate -1/2, 0, and 1 on my x-axis. So let's call this 0, -1/2, and 1. Okay? And then I know I've got the order pair -1/2 and about 3.8. Okay, so let's say that is right here. And then we've got 0, 0, so that's here. And we've got 1, 3, so that's like right here. All right, so this first point is an inflection point, so we'll keep that in mind. The next point is a local minimum and an inflection point, and then here we have a local max, all right? Also, we know it's not differentiable here, so it can't be a smooth curve. So we'll see what happens. All right, so starting to the left of -1/2, our graph is decreasing and concave down. So that means it's decreasing to this point and concave down. Now we have an inflection point because immediately after this ordered pair, it goes to concave up, but it continues to decrease. So it needs to decrease down to 0, but now it's going to bend the other way and turn to open upward like this. Now, I'm going to be a little bit more, so what I'll do here is something like this. And then to make it not differentiable, I'll actually make this a sharp point. But you could potentially have a sharp point and a vertical tangent line, perhaps, something like that. You could plot more points to kind of see what's going on there. But we're concave up to here. And then after 0, we're concave down and increasing to this point. So it switches concavity now, and it's increasing. And then after that, that's a local max, right? That's a local maximum. And then after that, it's going to start decreasing and be concave down. So it's going to do this kind of thing. And in fact, if you look at this, the x-intercepts would be 0, and if you solve this for x, you would get 2.5. So it happens to be that this x value here is 2.5, if you want to know that also. So this is kind of an interesting graph dealing with these rational or fractional exponents, some fun derivative stuff here with factoring and finding critical numbers, and seeing how to apply concavity and increasing and decreasing.